Welcome to the deep dive. Today, we're really getting into something foundational, something that powers so much of our digital world. We're talking GU Linux. And specifically, what it really takes to master it, maybe even up to the level of a Red Hat certified system administrator, the RHCSA.
Okay.
This deep dive, it's all about helping you get properly well-informed on this topic. It's everywhere.
Yeah, absolutely. And our mission today, basically, is to unpack the core pieces, the components that make the GNU Linux operating system, well, work. We're drawing heavily from this great article, the first in an RHCSA prep series.
Okay.
And it's interesting how it was put together, too. Use some pretty advanced tools, large language models like Mistral, Quinn.
Oh, cool.
Yeah, via Hugging Chat, and academic sources from places like core.ac.uk. So it's got a solid research base behind it for our exploration.
That's good to know. And why should you listening care about this? Well, maybe you're thinking about a certification like the RHCSA. Our source, it calls the exam very difficult, a real benchmark.
It is tough, definitely.
Or maybe you just want to understand, the backbone of the internet, cloud computing. Even those smart devices in your home. This deep dive, it'll give you those crucial insights. It's about getting past the surface, really seeing what's under the hood.
Exactly, understanding the why and how.
Okay, let's unpack this journey then into the heart of GNU Linux and what it takes to be an RHCSA. So GNU Linux, we say it's an operating system like Windows, like Mac OS, but it's built differently, right?
Yeah, fundamentally different in some ways.
Our source breaks it down nicely. 9 core components. And right at the absolute center,
Yeah,
the Linux kernel.
that's the core.
If the OS is a body, is the kernel the brain? What's its role, really?
That's a good analogy. It really is the brain. It's the central program managing the system's most critical resources. Absolutely vital. Think memory management, making sure apps get the RAM they need, and efficiently. And process scheduling. That's about deciding which program gets the CPU's attention when, so everything feels responsive. Especially, interactive stuff.
Right, so your typing appears immediately.
Exactly. And it's the main interface for device management. Talking to your hard drives, your network card. The kernel handles that translation, so your apps don't need to know the gritty hardware details.
Okay, so it manages hardware, memory, processes, and it handles different file systems, too, like XT4, XFS, even NTFS.
Yep, it abstracts that away. Plus networking stack, security features like access controls, even tower saving.
And the source mentions its modular architecture. Why is that so important, that modularity?
It's a game changer, honestly. It means you can load and unload pieces of the kernel modules dynamically.
Without rebooting.
Without rebooting or recompiling the whole thing. Think about adding support for new hardware on the fly.
Wow, okay.
It's not just convenient, it's a core design principle. It lets Linux scale incredibly well from tiny embedded systems.
Like in a smart thermostat.
Exactly, all the way up to massive supercomputers.
Yeah.
That adaptability is huge compared to more monolithic systems. And it supports things like real-time scheduling for, industrial control systems where timing is critical.
And how do regular programs talk to it through these system calls?
Precisely. System calls are like a secure menu of services the kernel offers. Want to allocate memory? Read a file. There's a system call for that. It's how your web browser, for instance, safely asks the kernel, hey, can you save this downloaded file for me?
Got it. So the kernel's the brain.
Yeah.
What about the tools we actually use to interact with it, the hands-on stuff?
Right. That takes us to the user utilities. These are mostly the command line programs that users and especially administrators rely on. The source highlights 2 main sets.
Yeah.
The GNU core utilities, core utils, and util-linux. Between them, you're looking at hundreds of essential commands.
Hundreds, wow. Like L's for listing files, .cp for copying.
Yep. Core utils alone has about 102 commands like those. Chmod for permissions. These are the absolute basics for interacting with files, text, directories, your daily drivers on the command line.
Okay. And util-lins adds even more.
Another 107 or so. And these are often more system-level things. Mount for accessing file systems, fdisk for disk partitioning, PAAS to see what processes are running.
For someone studying for the RHCSA, knowing these inside out must be non-negotiable.
Oh, absolutely fundamental. For daily tasks, for troubleshooting, You live and breathe these commands. And they mostly follow POSX standards, which means they work consistently across different Linux-like systems. They really bridge that gap between the kernel's power and what the user needs to do.
And people automate with them using scripts, right?
Exactly. Shell scripting combined with these utilities is incredibly powerful for automation. That's core sysadmin work.
Okay, so from the basic tools to, well, the heavy lifters.
Yeah.
Server software, this is where Linux really dominates, right? Powering the internet.
Yeah, this is a huge part of the ecosystem. Server software is all about providing services over a network to potentially thousands, millions of clients. Think web servers like Apache or Nginx, databases MySQL, PostgreSQL, email servers like Postfix, Samba for sharing files with Windows machines.
Right.
These usually run as daemons in the background.
Daemons.
Yeah, just processes that run constantly, listening for requests, doing their job without needing someone logged in directly interacting with them. They're often managed by systems like Systemed these days.
Okay, so they handle requests, manage access, security.
All of that. They're designed to be robust, secure, and handle, well, massive scale. The source mentions Google, Facebook.
Yeah.
They rely heavily on Linux.
Which creates that demand for skilled people, like RHCSAs.
But precisely. They need to integrate with firewalls, maybe iptables or NF tables, support remote management via SSH. And it's not just web or databases. Virtualization with KVM, container platforms like Docker, cloud infrastructure like OpenStack. Server software is key there too. It turns the OS into this incredibly powerful service delivery platform.
Next up, shells. Okay, anyone who's ever typed into a black terminal window knows about shells. But what are they really doing?
So the shell is your command line interpreter. It's the direct go-between connecting you, the user, to the operating system kernel.
So I type else.
Right. The shell takes that else, figures out what program it corresponds to, translates your request into the system the kernel understands, sends those calls to the kernel to actually do the work, and then it takes the kernel's output and displays it back to you in the terminal.
So bash is the common one. Z-ish is popular too, Dak.
Exactly. Those are different shell programs. And they do more than just run commands one by one.
Like scripting, command history.
Yep. Scripting is huge for automation. History lets you recall previous commands. Tab completion saves a ton of typing. Managing background jobs.
Input-output redirection too, right? Piping output from one command into another.
Absolutely critical. That's what makes the command line so powerful, chaining these simple utilities together to do complex things. The shell really makes that possible, bridging what you want to do with what the system can do. Essential for sysadmins.
Okay, let's switch gears to how data gets stored. File systems. It all starts with that single /O, the root directory. It's like the starting point on the map.
It is. The file system provides that whole hierarchical structure, folders within folders, that organizes everything on your storage devices, like your hard drive or SSD. Its main job is managing how that information is stored, where to put new data, keeping track of empty space, making reads and writes efficient.
But it's more than just organization, right? There's metadata involved.
Oh, definitely. Metadata is crucial. It's the data about the data. Things like permissions who can read or write a file, timestamps, when was it created, modified, file size, and importantly, inode references.
The nodes, what are those exactly?
Think of an inode as like an index card for a file. It holds all that metadata and pointers to the actual disk blocks where the file's content is stored. It's the file's unique identifier to the system, vital for finding data and for security.
Okay, so that ties into security. The source mentions encryption, like LUKS, and access control lists, ACLs, for finer-grained permissions.
Right. Modern file systems have robust features. Encryption protects data at rest. ACLs go beyond the basic owner group other permissions. And journaling is another key feature for reliability.
Journaling. That helps prevent data loss after a crash.
Exactly. Before actually writing changes to the main file system structures, it logs the intended changes in a journal if the system crashes mid-write.
On reboot, it can check the journal and finish the operation or roll it back cleanly.
Precisely. Prevents corruption. And Linux supports a huge variety of file systems. You've got your standard local ones like XT4, XFS, network file systems like NFS for sharing across Linux Unix systems, or CIF SSMB for Windows compatibility, and even special ones like TPEFs, which lives in RAM for speed, or PROCIFs, which isn't real storage, but a way to view kernel information as files.
And how does the system handle all these different types seamlessly?
That's the job of the virtual file system layer in the kernel. It provides a single, consistent interface so applications don't need to worry about whether they're talking to XT4 or NFS or something else. It's all abstracted. Understanding this is key for an RHCSA setting up reliable storage.
Okay, VFS makes sense. Now, kernel modules. You mentioned these earlier, like plugins for the kernel.
That's a perfect way to think about it. Kernel modules let you add or remove functionality from the running kernel without needing a reboot or recompiling everything.
What kind of functionality?
Primarily device drivers. You plug in a new USB webcam, the system automatically loads the right module for it. Need support for a specific network card? Load the module. It also covers things like support for less common file systems, maybe NTFS or specific networking protocols, or even security frameworks like Linux.
So it keeps the main kernel lean, only loading what's actually needed.
Exactly. Keeps the core kernel smaller and more efficient. Resources aren't wasted on code for hardware you don't even have.
How do admins manage these? Is there a command?
Yeah, tools like modprobe are used to load, unload, and query modules. And during boot, there's something called an initramps.
An initial RAM disk.
Right. It's a small, temporary file system loaded into memory very early in the boot process. It contains essential modules, like for your disk controller needed to mount the real root file system and continue booting.
Ah, okay. So it solves that chicken and egg problem.
Precisely. This whole modular approach makes the system incredibly flexible. Easier to update a single driver, easier to troubleshoot if a specific module causes problems. Great for tailoring a system.
There's something many users see every day.
Hmm.
The GUI, the graphical user interface, windows, icons, menus, makes Linux much friendlier for many people.
Definitely. The GUI abstracts away a lot of the command line complexity, makes
Yeah.
it more intuitive, more accessible. It's actually several layers working together. You have the display server at the bottom.
Like Xorg. Or Wayland now.
Exactly. X or the X Windows system was the traditional one. Wayland is the modern successor aiming for better performance and security. They handle the basic drawing on the screen and getting input from your mouse and keyboard. Then on top of that, you have a window manager. It controls how windows look borders, title bars, and how you can move, resize, minimize them.
And finally, the desktop environment. Like Genome, KDE, XSCE.
Right. The desktop environment pulls it all together into a complete experience. It provides the panels, the menus, file manager, system settings tools, application launchers, that whole cohesive look and feel.
And it's not just pretty pictures, right? Graphical tools can manage complex tasks too.
Oh, yeah. Tools like Genome Disks for managing storage partitions, or Network Manager for configuring Wi-Fi and wired connections. They provide a graphical front end to those command line utilities and kernel functions we talked about. Huge usability win for many.
So vital for desktop users, maybe less so for servers.
Often optional on servers, yeah. Many run headless without any GUI to save resources. But it's still important for admins to understand the GUI components, maybe for remote desktop sessions or managing specific graphical applications, and it allows for a lot of customization too.
Okay, moving on to libraries. You describe these as like pre-built Lego sets for developers.
Yeah, that's a great analogy. Libraries are all about code reuse and efficiency. They're collections of precompiled code that provide common functions.
Like math functions.
Yeah.
Or networking.
Exactly. Mathematical operations, string manipulation, file input-output, network communication, graphics rendering, instead of every single application developer writing that code from scratch.
They just use the library's version.
Right. It saves time, reduces errors, and standardizes how things are done.
Yeah.
A key concept here is dynamic linking and shared libraries.
Shared libraries, those .so files you sometimes see.
Those are the ones. So for shared object. With dynamic linking, the actual library code isn't copied into each application. Instead, when you run the application, the system loads the shared library into memory once, and multiple programs can all use that same loaded copy.
So that saves memory and disk space.
Tremendously. And it makes updates much easier. Imagine a security flaw is found in a common library, say, for handling images.
You just update that one shared library file.
And every application using it automatically benefits from the fix the next time it runs. No need to recompile hundreds of applications. Package managers like apt or DNF handle installing these libraries and managing their dependencies, making sure apps get the versions they need.
So it's crucial for keeping the whole system consistent and secure.
Absolutely. It's fundamental to how modern software ecosystems are built. Collaboration, updates, security libraries underpin so much of that.
Okay, last component, device files. These sound a bit strange. Letting applications treat hardware like .files.
It sounds strange, but it's a really elegant design from the early Unix days that Linux inherited. It provides a unified way for programs to interact with hardware devices through the standard file system interface: open, read, write, close.
So how does that work?
These special files usually live in the dev directory. They don't contain data themselves, but act as gateways to kernel drivers that talk to the actual hardware. They're broadly categorized into character devices and block devices.
Character versus block.
Character devices handle data as a stream of bytes, like a keyboard, mouse, or a serial port. Think Dev1 for a terminal. Block devices handle data in fixed-size chunks, or blocks, typically for storage like hard drives, DevSTA, DevNI VM11, or CD-ROMs.
So when a program reads from DevSTA, it's actually reading blocks from the hard drive via the kernel driver.
Exactly. And these files get created automatically when you plug something in. Mostly, yes. There's a system called udev, the device manager, that detects hardware changes, like plugging in a USB drive, and dynamically creates the corresponding device file in dev. It also handles permissions and can create persistent, meaningful names.
Okay. And each device file has, like, numbers associated with it, major and minor.
Right. The major number tells the kernel which driver to use, e.g. the SCSI disk driver, and the minor number tells that driver which specific device it is, e.g. the first partition on the second disk. And besides physical hardware, there are also pseudo-devices.
Like DevNull, the black hole.
That's the classic one. Send data there, it just disappears. Or devrandom and devrandom for generating random numbers. They act like devices but are purely software constructs provided by the kernel.
So it's a unified way to access, well, almost anything the kernel manages that isn't a regular file.
Pretty much. It simplifies things immensely for application developers. And for admins, understanding dev is crucial for storage setup, permissions, hardware troubleshooting, often done entirely without a GUI on servers.
Wow. Okay.
Yeah.
That was quite the tour. We went through the Linux kernel, the user utilities, all that server software, the shells, file systems, kernel modules, the GUI layer, libraries, and finally device files.
Each piece with its own job.
Absolutely. And see how they connect kernel at the core, utilities and shells to interact, file systems to store, modules to extend, libraries for apps. It builds that complete picture.
It really does.
And like we said, understanding this stuff isn't just for passing a tough exam like the RHCSA. It's for anyone who wants to be genuinely well-informed about the tech that, well, runs so much of the modern world.
Yeah, and if you think about the bigger picture, knowing these components, how they differ, how they interact, it lets you think much more critically about how systems actually work. You move beyond just being a user. You start to understand the mechanics. That helps immensely with managing systems effectively, with diagnosing problems.
Right. You can pinpoint where a problem might be. Is it a driver module, a file system issue, a library conflict?
Exactly. And you can better grasp how new technologies like containers or cloud platforms are actually built on top of these fundamental structures. They aren't magic. They leverage these core components.
So a final thought then for you listening. What does all this really mean the next time you load a web page or use a cloud service or even just interact with a smart speaker? How might knowing about kernels and shells and file systems maybe change how you think about how these things are designed or how they're secured or how you might troubleshoot them? These fundamentals, they really do underpin so much, and understanding them gives you, the user or the administrator, a lot more power.
Definitely something to reflect on.
Well, thank you so much for joining us on this deep dive today. Until next time, keep digging into what makes our digital world tick.